In this review lesson, we are looking at the difference between heat and temperature. Let's imagine that we heat two beakers of water. One is a large beaker of water and the other one is a small beaker of water. Both beakers are heated for the same time with identical Bunsen burners. Which beaker has the greatest amount of heat energy? Is it the large beaker, the small beaker, or are they the same? Well, you should have said they have the same amount of heat energy because they received identical heat from identical Bunsen burners that were burning for identical lengths of time. Here is another question. Which of the two beakers has the highest temperature? The answer is the small beaker. The reason for this is that in the small beaker there was more energy per molecule. This leads to the definition of what temperature actually is. Temperature is actually the average speed of the molecules. In the case of the small beaker, each molecule had more energy than in the case of the large beaker. Therefore, the molecules were moving faster in the small beaker than the large beaker, meaning the small beaker had the highest temperature. Let's look at temperature scales. An arbitrary scale is one where the scale is based on one chosen point at random. In the case of the Celsius scale, otherwise known as the centigrade scale, we choose the freezing point of water and the boiling point of water. The freezing point of water was made 0 degrees centigrade and the boiling point of water 100 degrees centigrade. And then the distance between them was evenly divided up. A better scale is the Kelvin scale. The Kelvin scale is based on the motion of the particles. So the lowest temperature on the Kelvin scale, 0 degrees Kelvin, is the temperature at which the molecules are not moving at all. This is the lowest temperature that you could have. This is known as absolute zero. This is the equivalent to minus 273 degrees centigrade or degrees Celsius. From that point, the scale matches the Celsius scale. So for example, a temperature of 0 degrees Celsius would be the same as 273 degrees Kelvin.
Absolute zero is the holy grail of temperatures. But even though we know exactly how cold that is, negative 273.15 degrees Celsius, reaching it has eluded us for centuries and will continue to elude us probably forever. For this frustration, we have to thank Sir William Thomson, first Baron Kelvin, who in the mid-1800s tested a new theory that heat is just molecules moving around in a substance. So he wanted to get stuff as cold as he could get it. So he conducted experiments that drew heat from a warm substance toward a cooler one and found that at some point, all the kinetic energy could be drained from the warm substance. It could no longer be cooled any further. This temperature wasn't like melting points or boiling points, which change for every substance. It was the same for everything. So Kelvin created a thermodynamic temperature scale that measured the amount of kinetic energy within any given material, and we still use his Kelvin scale today.
We are used to measuring temperature with thermometers. But another way of measuring temperature is to use a special infrared camera. And in an infrared camera, the temperature is represented in what is called a thermogram, an image where the temperatures are shown by different colours. In this particular thermogram, we can see that temperatures over 34 degrees centigrade are represented by white, whereas a temperature of 29 would be represented by dark blue. Thermograms can be useful. One use of thermograms is in diagnosing breast cancer. In the area of a tumour, the temperature will be warmer than the surrounding tissue. This can be shown up in the thermogram. Watch the video coming next.
The human body is thermally symmetrical, and the images shown are normal thermal patterns that are constant and repeatable. Thermal imaging is especially appropriate for younger women between 30 and 50, whose denser breast tissue makes it more difficult for mammography to detect suspicious lesions. This test can provide a clinical marker to the doctor that a specific area of the breast needs particularly close examination. Digital infrared thermal imaging detects the subtle, physiologic changes that accompany breast pathology, whether it is cancer, fibrocystic disease, an infection, or a vascular disease. Doctors can then plan accordingly and lay out a careful program to further diagnose and/or monitor until other standard testing becomes positive. This allows for the earliest possible treatment. The image here shows a 37-year-old patient presented for routine thermographic breast screening. She was not in a high-risk category. The vascular asymmetry in the upper left breast and the local hypothermia at 11 o'clock was particularly suspicious, and subsequent clinical investigation indicated a palpable mass at the position indicated. A biopsy was performed and a DCIS of 2 centimeters was diagnosed.
Another use for a thermogram is for seeing where a house is losing heat. Heating a home is very expensive, so it is useful to know where heat is being lost. Watch this video to see where a house is losing heat, as shown by a thermogram.
In the thermal images, warmer objects show up as red or dark orange, while cooler objects are yellow, green, or blue. The coldest objects are purple and black. Here the camera shows significant heat loss occurring at the 2 lower left windows and the front door, all showing as brilliant red-orange. These 2 single-pane, double-hung windows are reading an exterior temperature of approximately 40 degrees, which is well above the outdoor temperature, indicating rapid heat loss, with room heat easily passing through these windows, heating the glass as the heat is lost to the outdoors.
When objects cool down, they do not cool down evenly. In other words, they do not cool down linearly as a straight line. Rather, we always get what is called a cooling curve. Why is this? Let's consider a conical flask of boiling hot water in a room at 20 degrees centigrade. At the beginning of the experiment, there is a difference of 80 degrees centigrade between the water in the flask and the air in the room. A lot of heat will lose the flask rapidly because heat goes from a hot place to a cooler place. The temperature will drop rapidly. As time goes on, the temperature of the water in the conical flask is getting lower. So maybe a few minutes later, the temperature in the flask is now 60 degrees centigrade. That is only 40 degrees centigrade higher than the surrounding air. Heat will continue to move from the conical flask to the air, but because the difference is now only 40 degrees centigrade, it will lose heat more slowly. So the gradient of the curve will become less. This will continue until eventually the temperature of the water in the flask is identical to the temperature of the room. Heat will stop moving from the water to the room. Therefore, the line will flatten. Specific heat capacity is the energy in joules needed to raise the temperature of either 1 kilogram or 1 gram of the material by 1 degree centigrade. A material with a low specific heat capacity, for example mercury, will heat up very quickly. A material with a higher specific heat capacity, e.g. lithium, will take more energy to raise by 1 degree centigrade. It has a higher specific heat capacity. In this simple experiment, we are heating water and oil with identical heaters and identical mass of liquids. As we run the experiment, we see that the oil is heating up faster than the water. Why is this? It's because the oil has a lower specific heat capacity than the water. Therefore, its temperature will rise more easily. It requires less energy to reach the same temperature. Let's imagine that we had 2 beakers of water and the other of oil. Let's imagine that both are at 80 degrees centigrade. Which one contains the most heat energy? It must be the water, because to get the water to 80 degrees centigrade required more energy to go into the water than it did to get the oil to 80 degrees centigrade. Let's consider this situation. A beaker of water containing 200 grams of water and another beaker containing 100 grams of water. Both are at the same temperature. The large beaker has twice the mass of water and it is the same temperature as the smaller beaker. Therefore, it must contain twice as much energy. The equation we have to use when working out specific heat capacity, energy and mass is energy equals mass times specific heat capacity times temperature change.